Let's show that the work used to charge a capacitor is stored as potential energy in the capacitor, given by the square of the charge on a plate divided by 2 times the capacitance of the capacitor. Well, to begin, let's qualitatively talk about what is involved in charging a capacitor. A battery provides the ability to do work, to move charge from the negative plate of our capacitor to the positive plate of our capacitor. So let's say this is our battery. The negative terminal of the battery is down at the bottom, and the positive terminal of our battery is up at the top. We know that charge will move from high potential to low potential. So what that means is for this initially uncharged capacitor, the battery will provide that potential difference, causing a small amount of charge to be moved. And this small amount of charge will move from the negative plate of the capacitor through our battery. Our battery will then do work in order to lift this positive small amount of charge from low potential to higher potential. Because when this positive small amount of charge dq would naturally go from high to low potential, well, when we're in the battery, we are going from low to high potential. That low to high potential requires some amount of work to lift the charge up. So that amount of work is provided by the battery. And then once that charge is lifted to the positive terminal, it can then continue around in the circuit to get to the positive plate of the battery. So we need to do amount of work to deposit that small amount of charge. And this allows us to continue the cycle. We could take another small amount of charge at the negative plate, move it to the negative terminal of the battery, lift it up to the positive terminal of the battery, and allow it to fall, so to speak, to the positive terminal of the capacitor. And the battery allows this until we can't deposit any more charge on the positive plate, because it would require larger and larger amounts of energy to accumulate more and more charge. So there's going to be a capacity for that. Now, here's the main point that I want you to get right now. It takes work to move charge from the negative plate to the positive plate. Well, let's look at that. We know our goal is to find the potential energy stored by the capacitor. And that potential energy stored by the capacitor is really the energy shared between the charges on the positive plate and the negative charges on the negative plate. If we look at potential energy and work, remember, we had said work is equal to negative the change of potential energy caused by Let's look at the relationship between work and potential energy, because we know it takes work in order to lift charge up through the battery. It takes work to put charge on the positive and negative plates. And that work that we put into the positive and negative plates allows us to store potential energy. Well, let's go ahead and look at the magnitude of how much work and how much potential energy is stored in our capacitor. So from now on, I am just going to use W for work and just delta U and not worry about the signs, because we're going to focus on this qualitatively with the absolute value of those two quantities. So I guess what I'm saying is we're calculating how much work, or rather how much potential energy is stored by the capacitor. Well, we know that it takes a small amount of work to deposit a small amount of charge. We also know that there is a relationship between work and potential energy. So if we have a small amount of work, that corresponds to a small amount of potential energy, which corresponds to a small amount of charge. Well, there's a relationship between potential energy and charge, and that relationship is given to us via voltage. Remember, potential energy is charge times the potential difference. So here we have the small amount of potential energy is equal to the charge times a small amount of voltage. Now this charge here, this is the instantaneous charge. This is how much charge we would need to give us a certain amount of potential energy based off of the potential difference established. Well, let's go to our Valley College is quaint. Valley College is quaint. Well, if capacitance is a constant, and for this scenario it is, that means a small amount of potential difference times the capacitance is equal to a small amount of charge. Or a small amount of potential difference is equal to a small amount of charge times 1 over the capacitance. Well, putting this together means we have a small amount of potential energy is equal to our instantaneous charge on the plate of a capacitor times 1 over the capacitance times a small amount of charge. We now have an expression for potential energy. That potential energy is equal to the charge on a plate over the capacitance times a small amount of charge, that small amount of charge that we lifted. We could use this expression now to determine how much potential energy is stored in a capacitor. All we have to do is integrate both sides. So for the left side, we're going to say from some value of 0 for potential energy. We'll just, since potential energy is an energy of relative position, we will assign the 0 for potential energy to be the negative plate of the capacitor, which means the value of potential energy is going to be from the positive plate of the capacitor. So I'll call that U sub C. So we're going to integrate the potential energy from 0, from the negative plate, to the positive plate, which we're going to say is at the value U of C. For charge, we are starting out with a small amount of charge, so small that it's infinitesimally small, 0. And we're ending up with a charge Q on our plates. So when we integrate this, we get that the potential energy from the negative plate to the positive plate is equal to 1 over C, which is a constant, times Q squared over 2 when we integrate charge with respect to itself, from 0 to the amount of charge that's on our plate. And this then becomes the electric potential between two plates is equal to 1 over 2C times Q squared minus 0. Or in other words, we now have the potential energy stored by our capacitor. the potential energy stored by our capacitor is equal to the charge on a plate squared divided by 2 times the capacitance of our capacitor. Now that we know that the potential energy stored by capacitor is related to the amount of charge on our plates and the capacitance, we could use this result to express our potential energy in different forms. For example, let's see what happens when we use the expression Valley College is quaint. So when we substitute this expression into our formula for potential energy, we get the potential energy of the capacitor is equal to, well, the charge is the potential difference times the capacitance squared over 2 times the capacitance. Well, notice that a capacitance in the numerator will cancel with 1 in the denominator, leaving us with 1/2 times the capacitance times the potential difference squared. So here is our second way of expressing the potential energy of a capacitor. If we know the potential difference across the capacitor, and if we know the capacitance, this gives us our potential energy in terms of those quantities. And now let's do one last thing. Let's find the potential energy in terms of charge and the potential difference. So this again is just starting with Valley College is quaint. But this time, let's express capacitance in terms of charge and potential difference, essentially the definition of capacitance. Let's take this expression and plug into what we derived for the potential energy. So when we do that, we get, in the numerator, we have charge squared. In the denominator, we have 2 times the capacitance, which in terms of charge and potential difference is the ratio of the charge per potential difference. A charge in the denominator cancels with the charge in the numerator, and we end up with the potential difference, or rather the potential energy of the capacitor is equal to 1/2 times the product of the charge on the capacitor and the potential difference across the capacitor. These 3 results can be used interchangeably to determine the potential energy stored by a capacitor.